Okay, so if you're joining us now, good for you for being here. I just want to point out that on the Monday today, the clock page, solubility rules and more nomenclature. This is going to be the same worksheet that is renamed and called skill for the skills practice this Wednesday. So if you were to print that out and then as we answer them, record the answers, we probably won't do all of them, but whatever ones we do, you've already done. And that's always nice. Okay, so what we're doing right now is solubility rules and more nomenclature, which you probably want to download. That's going to be a skills worksheet for this week. And so all the things we're doing right now are going to save you some time. You'll turn them in later. And the next thing is to do this, you need table 5.1 in the text, section 5.4. Now we're in chapter 4, which is writing and using balanced chemical equations. But the lab this week, I believe, involves you using droppers and a spot plate in your kit to make precipitates form. And so a precipitate is just a fancy word for a solid. I had two solutions that were both clear. In this lab, I think for us, they're clear and colorless, but they don't have to be colorless. And when you mix them together, if you see anything that interferes with light, if it looks, it doesn't have to look like a rock came out of nowhere, that kind of precipitate. It could just be, it was clear, but now it looks cloudy. That cloudy is a precipitate. It's a solid that's forming in solution that over time will settle to the bottom of the spot plate. So because that's the lab that you're going to do starting Wednesday for this next coming up week, I thought it would be good for us to meet this table. So I go to my Pearson text, and in table 5.1, it talks about some general rules of solubility. I'm just going to grab those real quick. And then you might screenshot it. I can't keep it up for you and do what I need to do in front of you. I'm just showing you where it is. Okay, so here's the table. It just says solubility rules for ionic compounds in water. So right now, the worksheet we're looking at, we're really focusing on ionic compounds. How do you know it's a compound? More than one capital, no charge showing. How do you know that it's ionic? It starts with a metal or ammonium ion. And then there's some general rules. So lithium, sodium, potassium, and ammonium. Those aren't the only ones. When I'm using the actual real periodic table, it's all the alkali metals. Now, hydrogen is not an alkali metal, so hydrogen is not part of this. But lithium, sodium, potassium, rubidium, cesium, and francium, and ammonium are all soluble salts. If that's the cation, there are no exceptions. If you're only going to memorize like a couple rules, and over time by using them, you will memorize these rules, the first one's important. Nitrates and acetates, no exceptions. They're all soluble. What does soluble mean? It goes into solution and I can't see it. It dissolved. Soluble means it dissolved. Now, chlorides, bromides, and iodides, those are the halides. It really is just those. The line leader there, fluoride, is so small and electronegative. It is such a special element that this rule does not apply to it. We're not going to deal with fluorides. So for chloride, bromide, and iodide, when these things are typically soluble, which means they dissolve. And if it's ionic and soluble, it dissociates into ions. But there are 3 exceptions: silver, mercury 1, and lead 2. And so over time, you will just sort of know those are the exceptions. They won't catch you off guard. When you're taking Chem 1B, if you go that far, you'll need to memorize that. Okay. Then sulfates are generally soluble, but it has a few more exceptions. When sulfate pairs with strontium, barium, lead 2, silver, or calcium ions, it does form a solid, a precipitate. Now, as far as compounds that are insoluble, which means I could put this in water and it doesn't dissolve, like if you put sand in water, you can still see the sand. Hydroxides and sulfides are typically insoluble. Carbonates and phosphates are insoluble. So when you look in your kit for the experiment that you're going to do this week, when you look at the names and the formulas, when you see carbonate and sulfate, or when you see phosphate and carbonate, you're going to think, oh, those are probably insoluble. They're not going to dissolve. So the label might say sodium carbonate and it's dissolved, and then you'll have something else. But as soon as you mix them together, probably a carbonate is going to precipitate, because the only exceptions are group 1 metal ions and ammonium ion. So I'm going to use this table now and show you how this gets filled out. In lab this week, we're going to be exploring solubility rules, and this skill worksheet is meant to reinforce that concept and prepare you for writing total and net ionic equations. So we're going to use this table in the text to answer these questions. The first is just a practice for nomenclature. So for potassium sulfate, I think to myself, potassium's a +1, sulfate's a -2. I'm going to need 2 potassiums. And I have the formula. We're going to continue to work on nomenclature, and when I'm not testing it, I can use the actual nomenclature, which is good reinforcement to help us learn this. Is it ionic? Well, yes, because potassium is a metal. If it's ionic, is it soluble? And now we go to the table. Sulfates are generally soluble. Potassium is not an exception. Potassium salts are always soluble. That was the first rule we met. So the answer is yes, it is soluble. If it is soluble, it dissociates into ions. What ions? The ions that it was made from. So you can either put potassium ion and sulfate ion, or you can be a little bit more specific and say, well, there's 2 potassium ions. But the ions that you used to build the formula are the ions that it's going to break into. It doesn't break into, oxygens and sulfurs. Sulfate is a chunk that is covalently bound and it sticks together. Okay, the next one, ammonium nitrite. Ammonium is the adopted group 1 metal ion. This is a soluble salt. As soon as I see a group 1 metal ion or ammonium, I know it's going to break into ions. Nitrite, I didn't memorize, but I know nitrate. Nitrate is NO3 -1. And the ite is going to be 1 oxygen fewer. And it's a +1 and a -1. They come together in a 1-to-1 ratio.
Hey, Sue.
Uh-huh.
For the classify part, are we putting yes or are we putting ionic or covalent in that box?
Either one. Since I said, oh, you're right. I should probably put ionic. I like your answer better. So here I'm going to say ionic. Ionic. So you can put an I or a C. Okay, so if you just walked up to this, that's a lot of letters and numbers, and it might be a little bit daunting. But because you know nomenclature, you know that it's just 2 chunks that came together. It's just both the cation and the anion are polyatomic. That's why it looks so complicated. Okay, so those are the ions that it's going to break into. Okay, so I'm going to come down here a little bit farther, go to phosphine. Phosphine is one of the 5 covalent compounds that have a common name that we need to know. Right now, let's make a list in our head. What are the other ones? Water. I love water. Ammonia, phosphine, hydrazine, and methane. So when we meet these covalent compounds that contain hydrogen that have a common name, we have to recognize them. So phosphine is covalent, and it's one that we memorized. And so if it is soluble, if it is ionic, is it soluble? It's not ionic, so I'm not going to answer those questions. Okay, let me do lead 2-phosphate right here. So lead 2 is a cation and phosphate is an anion. And they're going to come together in a 3-to-2 ratio, so +6 and -6. That is ionic because lead is a metal. But phosphates are generally insoluble. Which phosphates are still soluble? Alkali metal and ammonium. So this is insoluble. If it's insoluble, it doesn't break into ions. So don't write the ions in the last column. Does that make sense?
Can you repeat that?
Sure. If it's insoluble, that means it doesn't dissolve. And if it doesn't dissolve, it can't dissociate, break into ions. So don't write the ions in the last column.
Okay, thank you.
You're welcome. Okay, so it gives us a chance to practice some nomenclature. And basically what we're doing is, if it's ionic and soluble, we're breaking it into the ions that it's made from. For chapter 5 and what we're doing this week and writing ionic equations, complete or total and dead ionic equations, which you haven't been introduced to yet, you really need to recognize, oh, that's ionic and it's soluble, and be able to break it apart. Here in the name or in the compounds, like we don't talk about the charges, we don't show the charges, but when the ions are floating free in solution, they do have charges and you need to show the charges. So that's the first side. And then down at the bottom is, oh, it should say there is a side 2, and here it is. There is another page. It ended up on the wrong page. Oops. Okay, so we're gonna cover acids separately. Acids are covalent. So when we talk about compounds, we could say there's 2 general categories. There's ionic and covalent. This is super important for our class. So ionic compounds are made from ions. Covalent compounds share electrons. There is a subcategory of ionic compounds that we call, every ionic compound is called a salt. So table salt, sodium chloride, is one of a zillion salts. But there is another category. If the salt has the anion that is hydroxide, that is called a base. So salts and bases are ionic compounds. And this base that I'm referring to are the kinds that contain hydroxide. And then for covalent compounds, those are molecular molecules. But there is a subcategory. And a subcategory, so we could talk about covalent in general. That's most of them. But if it begins with an H, it's an acid. If it begins with an H, and it's one of the 6 that has to be bubbled through water, it's an acid. So I just want to remind you that there are 6 that could either be pure, they're gases, or they could be bubbled through water and they're aqueous. When they're bubbled through water, those are acids. So if I had, for these 6 only, if I had a G behind it, it would be classified as covalent. But if I have an AQ behind it, it would be classified as an acid. As covalent, we say hydrogen something, hydrogen fluoride, hydrogen bromide, hydrogen cyanide, hydrogen sulfide. But as an acid, these 6 become hydroic acids, hydrofluoric acid, hydrocyanic acid. Okay, so I'm not going to be dealing with the ides that make hydroic acids at this moment. I want to talk about the other kinds of acids. So you know that acids, come from anions gaining hydrogens, and the anions could be ides. They make hydroic acids, or ates, or ites. So when the ides are aqueous, and then for the ates and the ites, always they are named as acids. They are classified as acids. So I could say there's two general categories of compounds, ionic and covalent. Or I could say there's four kinds of compounds: acid, base, salt, and molecular. Okay, so for here, we're going to practice naming our acids. All of these begin with hydrogen. And you'll notice that I have put an AQ if it has a possibility, if it's one of the six, that could be pure and be covalent and called hydrogen something. But for the other ones, I don't need the AQ. They're compounds, they're eights and ites that begin with a hydrogen. They're always acids. So we take off the first part and see what's left behind. I don't recognize that, ClO4 minus. But I do know chlorate is ClO3 minus, and this is one more. So this is perchlorate. And it has become an ic acid. Perchloric acid. Perchloric acid is important because it is one of the six strong acids, strong enough to stand alone. They are ionized by water 100%. And we'll talk more about this in a week. So there are, but of all the acids, only 6 are ionized completely by water. Ionized completely means it's like they dissociated into ions. But they didn't dissociate into ions because they're not made of ions. Water pulled them into ions. And that's why we use the word ionize instead of dissociate. But whatever you say, they're broken into ions. So for perchloric acid, because it's one of the 6, it's a strong acid. And if it's a strong acid, it's pulled into ions, and the ions are hydrogen ion and the rest of it. And that is always the pattern for acids. If it's pulled apart, it's pulled into one hydrogen, and then everything else. Pull off both H's and see what you have left behind. That's carbonate. I'm pulling off both hydrogens because I want to look at the anion and to see if it's an ide, an ate, or an ite. And this is an 8, and 8s make ic acid, so carbonate becomes carbonic acid. Is it strong? Let me see. Hydrochloric, hydrobromic, hydroiodic, nitric, perchloric, sulfuric. Nope. There are only 6 strong acids. If it is a strong acid, what ions are present? Well, it's not a strong acid, so that answer does not apply. Does that make sense?
Yes, thank you.
Okay. The only one I want to show you, and then we can work on this and check answers, check back together, or you can just leave. This is your skills worksheet for this week starting Wednesday, is sulfuric, because sulfuric is a little unusual. Sulfuric acid is a strong acid, but only the first proton is strong. First proton only. So I showed you what the products were because sometimes, and it's understandable, I know why students do this, but students will break it apart like this. And that's not right. Only one hydrogen breaks apart. The other hydrogen stays with the chunk. Now, why do students do that? Because that's how we decide the name of the acid, is to pull both hydrogens off. So it makes sense, but the water doesn't pull both hydrogens off, just one. Okay, so at this time, here's what I suggest we do. I'm not gonna stick you in breakout rooms, but I suggest right where you are, just work on it. And then when you have a question, say, hey, Sue, let's do this one. And I will do them for you. I will talk you through them. Or if you've gotten all you need, you can leave.